In this video, I'm going to tell you about best case and worst case analysis. Now, since we are done with the asymptotic notation, we are done with the time complexity analysis. So, next thing that comes here, what is best case and worst case? Now, in ideal scenario, in general terms, if I just talk to you about the best case, if I just normally write here, let's not firstly talk about in context of the programming. If I talk here in the context of worst case, I'm just here simply, basically, I'm here talking about a very general. I will take one real life example, and with the help of that, I will try to make you realize what actually these two terms actually mean. So, when we talk about best case and worst case, like I must have taken, I think, this particular example in my one of the previous videos of type complexity, that you are at one place and that place is A, and you have to go to another place. Supposedly that place is B, and this is you. This is you. So now you have to go. Now you have the option. One way is this. One way is this, and one way is this. Now supposedly the middle one, this way, is actually the shortest, since it will take less time and it will have not have those external constraints. Now external constraints here means traffic and all. This won't. So this is the shortest. Now, if I come to this, and supposedly I realize that this particular path, that this path is actually the longest. It will take a lot of time and it is also equipped with external constraints. So now, if I ask that for this particular person, that for the person who is standing here at A, what will be the best case? So the best case would be if that person goes through this middle way, the way that here, supposedly this is the way. So the best case for this particular person will be that if he goes through this way. And what would be the worst case for this person if he prefers to go by this particular way, the third way, which is actually the longest. Now, so I repeat it again that for this particular person who is standing at a particular place and if he wants to go to another place, so for this particular person, the best case would be if he prefers the shortest path, and the worst case would be if he prefers, or even if he doesn't prefer, he goes with that by the longest path. That will be the worst case. Now, when we talk about the best case and the worst case, now where comes what will come in between? So in between comes an average case. Now, what is an average case? If this path is the best one, if this path is the worst one, then this will be the average path. This will be what? This will be this path will be the average path. The topmost path in the context what I am talking here will be the average path. Now, what does average path means? Average case means rather. This will be the average case. So how did I classify this in context average case? So let me tell you how we classify. So this path won't take a lot of time, but it also won't take a very short amount of time. It will take somewhere in between what these two paths are taking. And eventually you will realize that this path will take average time and it is also like having some constraints, some little bit of traffic. So this is the average case. So this is the mean by average case. This is your best case. This is your worst case. Now, so hopefully these two terms are clear. And if I write the third term also, then I will be writing here. That is what average case. This will be average case. So now I will be coming to the topic, actual topic. What is best case? What is average? So firstly, I will be telling you about the best case analysis. So what does this best case is all about? Now, when you are actually analyzing best case, one of the examples that I would be taking about array, and not just simply we will be writing an array, but actually I will be telling you about the fact if we are doing searching in array. So how will you encounter the problem of best case and worst case? So supposedly this is your array, like our arrays of this kind only. It's a uh, size, it's a block, or you can call it is a block of contiguous memory locations. So these are those, and I write here 2, then I write here 10, then I write here 15, I might write 4, doesn't matter what the numbers are, and this is 20. So now, what is the best case one? We are doing the process of searching in which the value that we have to search is 4. So suppose that this is our task, that we have been given an array, and array supposedly this is our array, and our task is simply to find this key element. Now what we ideally do, we place the for loop iterator here, and we iterate through, and wherever we find it, we simply change the value of flag, that is the Boolean variable, and we just break the loop and we just find the value. This is the method that we ideally do. We traverse through the whole array. So is this the best case? Probably not. This is not the best case scenario. You are actually almost traversing through the whole array. So, like, what do? So now in next context, suppose the key is for the last case, the time complexity was big O of n for the last case. Now I have changed the value of key to 20. Now, in this case, what is happening? In this particular case, if you are just saying like what is happening here, so you are just simply saying that this particular function, like this particular array here, not function, sorry for the long word here, this particular array, if we just place our pointer here, and if we just traverse through the array, at the last of the array, we find the particular key element, that is 20, when we reach the last of the array. So this particular key element has been found in the array, but actually it is placed at the last index. So again, the function that I talk about, like I have mentioned this word a lot in asymptotic notations. So the function that I talk about here, bn. Now bn is a normal function. So that function will be n or n plus 1, whatever you call, and the time complexity would be big O of n. Now, supposedly, I was given, supposedly, if the key element was a number, and so if the key element was a number, 5, now the element is 5. Now, if we want to search through linear search technique, this is actually linear searching here. If we write here, everyone knows, I think it's a linear search technique. So in linear search, supposedly, if the key element that is supposed to be searched is 5, so how do we do it? Like we will again place at the pointer, the iterator at the first index, that is the zeros, and then we will traverse through the whole array. Even though the pointer, the flag value won't change, the boolean value won't change, but still you will have traversed through the whole array and you haven't found it. So again, this will be the scenario. The bn function would be equal to n or n plus 1, whatever you call. Since we all know that big O notation is simply like it's the degree of the polynomial. It's what the degree of the polynomial, and degree of the polynomial is simply the highest term. So it is like that. And now I would like to just this was actually your worst case. Okay, this is actually your worst case. Now, after explaining the best case as well, I will try to tell you this is your worst case. So don't get confused that this is your best case, or the best case is one when the element is found, and the worst case is when it is not found. This is completely wrong. Best case is associated with the fact of the case here. Best and worst simply mean like here, best and worst simply mean that both can be efficient, both are equally good to get the task done. When it comes to the context to get the task done, both are equally good case approaches. But which one is like better equipped? What will be the best technique for the person to do? Both are the options, but which one is the best? We do that. So that happens. Here, we whatever the case might be, even if the key element is there in the array or it is not there in the array, we have been traversing through the whole array. So that means the iterator of the loop, we were iterating from the first index of the array to the last. So eventually, the R function is what? It's n or n plus 1, whatever you take. So the time complexity would be big O of n. That is your worst case scenario here. Now, supposedly, I change the key element and let me do it. Supposedly, I change the key element to in 2. Now, if you see the key element and if you simply try to search it, so you will again iterate it from the first index of the array. And this time you don't have to traverse through the whole array. You will place the iterator on the first index of the array and you will find the value of Boolean changes that you have found the value. You have searched for it. So now what happened? Now this is actually the best case scenario that the value that you were supposed to search, you started searching through the array and you found it at the first index. So now the what will be our function? So in this scenario, our function would be, it would not be like n is n or n plus 1. Our function would be 1. So our function would be what? This would be 1. And therefore our time complexity would be, that would come out to be constant. This, oh, sorry, this would come out to be 1. This, this is now changed. Now I will explain you this once again that you were searching in an array through linear search technique. And you were given a key element. You did for the last element, you did for an element which was not present, and you even did for the element which was present in the array, but it was not placed neither on the first place or on the last. You even did for that. Now in this scenario, you were given a key element that was that you eventually found at the first index when you tried to traverse through the whole array. So eventually what you had to do, you completed the task, but you never had to traverse through the whole array. So what would eventually happen? That when you will try to write the function, this function is simply based upon the number of times you have iterated. So simply you will find that you have to just iterate one time, and therefore your function would be n, and your time complexity would be big O of 1. Sorry, your function would be 1. So I stand corrected here. The function would be 1 because you just iterated one time, and therefore your time complexity would be big O of 1. Okay. So now I'm telling you about like cases don't define which notation you would be using. Let me tell you, cases won't define which notations you would be using. I could have done here I could have done here like this. It would have still meant the same. It doesn't define that now this is the best case notation and the big O notation was the worst case notation. So actually notations are not dependent on the cases. You can use any. The thing is that you have to define it in a such a way that the meaning should be the same of the cases. Now, for most often than not, let me tell you, when you were studying about the notations, I just told you about each of the notation, what it actually symbolizes. So the big O notation was for the upper bound of the function, was supposedly for the upper bound of the function. So now, now when big O notation, you know that it is for upper bound of the function. So like when you actually try to find out the case analysis when you're doing. So in case of the worst case, now I'm not saying that big O can be only used, but I'm telling you why it is supposedly used commonly. So what is the reason? Because big O notation is actually for the upper bound of a function, and actually upper bound is the maximum, is actually the maximum time that it can be taken. Some the function's maximum value in a range when the function value is maximum. So in that context, in worst case, now worst case is what? Even in the worst case scenario, the job will be done in this particular time. This is what actually worst case analysis simply means. So it will be the maximum time. It will be what? It will be the maximum time. So just according to the notation, it will be the upper bound of a function. What? It will be actually the upper bound of a function. So therefore, big O notation is used in that context. But that doesn't mean for best case analysis, you can't use. I repeat, in worst case analysis, you tend to identify that in the worst case scenario, if I have to complete the job, how much time it will take. So you define it by the maximum time that it would take. So that is defined by big O notation, not just because it is supposed to be done, but actually it is like that. It is the maximum time. So it is the uppermost value, upper bound of a function. So therefore, big O notation is used, but that from nowhere means that you can't use omega symbol or for best case it can big O notation can't be used. Any notation can be used for any case. It's simply that cases don't define the notation. But commonly for analysis, we use big O notation. That is, you must have observed as well. So, like moving on. So now I will be going to explain you the best case and the worst case through another searching technique that you all know that is one is linear search and the other is binary search. But I won't try to explain you binary search on an array. I will try to explain you on a binary search tree here. So let me just make a binary search tree here. So this is 20, this is 10, this is 5, this is 4, this is 3, what this will be. This can be 15. These are normal numbers. This doesn't follow any trend. I'm not making like this. This is 25. So, all right. Now, this is what? This is a binary search tree, commonly abbreviated by BST. So, like, now we will be analyzing the best case and worst case here. We analyzed in linear search, and now we'll be analyzing in binary search. Or in a normal thing, the it's not the other technique, it's basically simply a binary search tree here. So how will we do? How will we do that? No. If you will realize that the topmost element of a binary search tree is known as root element. I'm writing here element, but it simply means element. This actually, the topmost element of a binary search tree is known as root element, and the last elements of a binary search tree, that is BST, are known as leaf elements. What they are known as leaf elements. So, if I have to explain you, the topmost element of a binary search tree is known as root element, and the last elements of a binary search tree are known as leaf elements. Now, in context of if I try to explain you, if I just try to say that I have to find an element, or I just say that this particular binary search tree is given to you, and you have to find the best case solution. What is the best case solution? So the best case solution is that you don't have to traverse through the whole tree, whole binary search tree. It's simply that you don't have to traverse through a whole tree. So the best case would be if you just iterate. We have seen that the best case would be if you just have to iterate simply one time. And in that context, your time complexity would be simply big O of n. Now, when will this thing occur? Like, when will this best case scenario occur in which the you will just be iterating for one time and that your time complexity would be, sorry, I have again written it wrong. Just correct it. This would be simply like this would be O of one. So when this particular scenario will be happening, in this particular tree, if you have to find this particular scenario in which you just have to iterate once, and eventually your time complexity will become big O of one. So if you have to search what? You have to search this particular root element. Now, if you have to search for this particular root element, you just have to iterate once. You have will be finding it. So I will be writing here when this scenario will occur. When throughout this video, if I'm using lm, that means element. Root element is search. So sorry for a little bit of pause. And now the best case scenario has been discussed. Like the best case scenario would be if we just have to iterate for one time. And therefore, the time complexity would be big O of one. And when this is obtained, like based upon the binary search tree that we have been given, when this best case scenario is obtained, like when we have to search for the root element, that is here 20. Now, what would be the worst case scenario? Worst case scenario is that when we have to search for, I presumably think the height. Let me tell you what is the worst case scenario. When we have to iterate it, when we have to iterate the given binary search tree, this is the thing. Like, what will be the worst case scenario here? Now, worst case scenario will be that you have to travel from the root element to the whole, like from root element to the leaf element. So, what you have done in that case, you have traversed through the whole binary search tree, and you have actually iterated for how many of times is equal to the height of the binary search tree. You have iterated for how many times equal to the height of the binary search tree. Okay. So in that case scenario, in that scenario, I am simply talking about if you're talking about in that case. So what we have to simply do, like supposedly I give you a task in that particular binary search tree that you have to search for the element 50. You have to search for the element 15. So 15 is present in the leaf node part, leaf elements. It is one of the elements. So if you have to search for 15, you can't simply get it at the top, or you can't somewhere from in between you can find it. You have to traverse from the root element to all the leaf elements, and there you have to find it. So in that process, you have actually traversed through the whole binary search tree. And the number of iterations that you have done is equal to the height of the binary search tree. And therefore, I have written the for worst case scenario, your function bn would be height of the tree, and height of the tree is given by log n. Simply, it is given by log n, and like if you just simply take here, what is the height of the tree? Height is 3, and the number of nodes simply, if you just take into account what are the number of what is the height simply. So height is 3, and that is clearly given by the fact equal to log n. That is clearly given by the fact equal to height is equal to log n. And when it comes to the context of searching, so if you have to search 15, like I told you, you have to iterate in such a way that from the root element you have to come to the leaf elements, and in that process you have iterated through the whole binary search tree, and the number of iterations that happened were like equal to the height of the binary search tree. They were equal to the height of the binary search tree. So in that case, the height is given by log n simply, and in that context the time complexity would be given by is equal to big O of, it will be big O of log n. We have to traverse through the whole of the binary search tree, and in that process, the number of iterations that happened were equal to the height of the binary search tree. And height of the binary search tree here in the concept is simply taken out, through the fact. Let me tell you. Here, the height of the binary tree is 3. So that 3 basically can be simply taken out from the fact log n. Now log n here, like I'm just telling you this concept that for height of the binary search tree, we normally use these kind of formulas like log 2 n plus 1 minus 1. This we use it normally. So in that context, suppose they were given in a given BS binary search tree. Now how many nodes are given? If you count, this will be 3 and this will be 4. So 7 nodes are given. Now, in that scenario, if we just place 7 plus 1 equal to 8, and in when the base is 2, then this will come 3. 3 minus 1, it will come simply like 2. So you don't have to take this 2. Yours is the answer is 3. So what we do, this particular formula which I have written in front of you all, this is a formula of a perfect binary search tree. This is the formula of a perfect binary search tree with n nodes. What with n nodes? PST is simply perfect binary search tree, and this particular formula is for that with n nodes. With simply n nodes. What is that? With simply n nodes. And if I tell you like the formula for which I have written the binary search tree, and that is also like in context for the worst case analysis. So that I would represent again write the value height. Here, this is just like the basic idea of the binary search tree. That is, I'm not covering here at the moment. That you will study when I will be like teaching you binary search tree. So here, I just simply tell you. So that formula is log. And just like in time complexity, I told you the base is actually subjective. So this is here log 2, log n base 2. What it is? It's log n base 2. So this is the formula for the complete. I will write here. This is the formula for complete binary search tree. This is the formula. This. So in this case scenario, in this case scenario, in the worst case scenario, suppose you were to, like in the best case scenario that if you have to search the root element, then you have to just iterate for one time and the time complexity will be big O of one. But if you have to search for the worst case scenario, then you have to traverse through the whole binary search tree and the number of iterations that will happen will be equal to the binary search tree's height, which is equal to log n. So time complexity will become big O of log n. Now, what is the modification here? Suppose if I am making a left skewed BST, what I'm making? Left skewed BST. Now, many of you will be having like a question that what is left skewed BST? So it is not anything different that much. Left skewed BST. Now, left skewed BST is somewhat like this. If I tell you like what? 2, 4, 1, 10, 9. This is 8 actually. This has become 8. I don't know. I wanted to write 8 here. This is 9. So in this process, you'll just find that the right half of the binary search tree, if you just take the root element as the reference, if you take what? The root element as the reference, so you will find the left half of the binary search tree is there, but the right half is not there. So this is the binary search tree with only left half. So therefore, this type of binary search tree is known as left skewed. So now in this process, if you have to, in worst case scenario, if even in left skewed binary search tree, if you are supposed to search the root element, then this will actually again be having the time complexity big O of 1. But in worst case analysis, if you have to search for the leaf element like 8 or 9, then you have to traverse through this whole like this. You have to do it like this. The number of nodes here, the number of nodes in the left skewed tree, you have to traverse for that. So in that case scenario, your time complexity would become big O of n. Now, n here simply represents the number of nodes in the left skewed tree. And if your function you have to ask, then it will become simply n. So this is the scenario. I hope you understood it. Now, if we come to the worst case analysis for BST, for worst case analysis of BST, so not the maximum, minimum time complexity if you find. The minimum time complexity is big O of log n, and maximum time complexity you will find is as n. So this is min, this is min, this is max, this is min, and this is max. This is for worst case scenario of the binary search tree. This is for what? This is for worst case scenario. This is for worst case analysis of binary search tree. This is like the minimum and this is the maximum. Based upon the priority chart also you can know. Now this n will happen when you are doing of the left skewed binary search tree, and this will come for log n would come for like a normal binary search. And the other thing is that I told you about correspondingly their functions like bn, what I am taking throughout this video. The bn would also be like that. In the first case for minimum would be log n, and the base 2 will also be there, but base is subjectively. I just told you in the time complexity also. And in this scenario for maximum scenario, in maximum scenario, what it will be? It will be n. So time complexity for that, when the function is bn is equal to n, time complexity will become big O of n. When bn is equal to log n, then time complexity will become big O of log n. Now, the last, just like I told you about average of the theta notation that represents the average of a function, the theta notation. So in that case, also in the similar case, average case analysis. What? Average case analysis. So for average case, you don't need to remember much. There is simply a formula which actually is not an applicable formula for each and every the case. Like for more complex situations, average we don't take. We simply take these two, best case and worst case, is equal to number of possible cases. This is number of possible cases upon number of cases. In other words, if I want to express this formula, then this formula would be simply b1n plus b2n plus b3n, so on, and upon it will be 1 plus 2 plus 3 plus so on. Now, what does the average case here means? So average case is like that, just like I told you, it is not the best case analysis, it is not it comes in the worst case analysis, it just comes somewhere between the worst case and the best case. So in this is the particular formula, but actually in very complex situations, we don't deal with the average case, we simply deal with the best case and the worst case. So the average case formula, if we just have to take out for a normal case, then average case formula is number of possible cases and upon number of cases. What is the formula? Number of possible cases divided by number of cases. Now, what does this exactly mean? I'm just telling you here. Like you have the functions of those possible cases. You have the function of those possible cases. Like for one case, the function is like b1n. For another case, the function is b2n. For the third case, the function is b3n, and so on b4 and b5 and whatever it is. You have to sum them of those functions and you have to divide them by the number of cases, like one, two, three, those cases notations. You have to simply do what? You have to divide them by those cases notations. So just like that, a more precise way of writing this is like that. The number of possible cases upon the number of cases. Now, number of cases is a constant, you know. Like number of cases will be what when it comes to the average? Because we are not dealing with a very complex situation, we can't take average of that. So this is basically for the simple thing. So number of cases will be what? Number of cases will be simply equal to n, and number of possible cases can be taken like b1n plus b2n plus b3 and so on, or you can take 1 plus 2 plus 3 plus, like simply that you are giving the value to those cases simply. Like I could have written like this: b1n plus b2n b3 and so on, simply so on till the time, like number of cases would be 1 plus 2 plus 3 plus 4 plus 5 plus. So this is simply the summation. It's simply the summation. And like the possible value of cases, you have to sum them up. Simply, you have to do what? You have to just sum the value. You have to just simply number of possible cases. Simply, what? You just have to simply do number of possible cases. This is what you have to just do: number of possible cases. And what is number of possible cases? Like the functions that you will get. If a particular case is there, then you will get a particular function known as bn, and you have to take out those values and you have to just sum them up. That will, when you sum them up, that is your numerator, and you have to divide by the number of cases. Now, number of cases ideally means what? They mean simply one. They mean what? They mean simply one, like that. So, just to avoid your confusion, I am just simply erasing this, and I will write it here only. This and this is simply the average case analysis. The number of possible cases, like how many cases are possible, you have to take out their particular functions like b, n, and in subscript you can use 1, 2, 3. So you can also denote it by n as well or x as well. And you have to sum those values. Whatever the particular b and values are there, you have to sum them up. You have to divide by the number of cases, and number of cases are n. So this was all about case analysis, like best case, worst case, and average case. So hopefully you understood that. Thanks for watching. Do like it, share, and subscribe. Thanks for watching. Stay tuned for more content. Thanks for watching.